I shall recall some well-known notions of arithmetic and hierarchy. I apologize for those whom it is trivially known, but I expected that there will be some philosophers here, so that I think it was reasonable to quickly recall some things. So, arithmetic has the language, as you know, is equality, constant zero, successor function, addition and multiplication. What you see here on this slide is axioms of so-called Robinson arithmetic. You see it is, in English we needn't read it all in details, but these are axioms about successor, addition and multiplication, only finitely many, and it's very, very simple axiom system. Parallel arithmetic results from Robinson arithmetic by addition of the axiom scheme of induction for each formula phi, also possibly know when phi is satisfied by 0, and for all x, when phi x then phi, the successor of x, then all elementary numbers satisfy the formula phi. Now, about arithmetical hierarchy. It concerns sets of natural numbers of since coded by this, and here boldface n is the standard model of arithmetic, and we formulate our survey in such a way that it is meaningful. Either we have arithmetic with function symbols or without by relations. Bounded quantifiers. Bounded quantifiers. For all x less than y, as it says, there is an x less than or equal y, are abbreviations of, as usual, for all x less than y. Phi means for all x, when x is less than of y, then phi, and so on. A formula is bounded if all quantifiers in the formula are bounded. Now, more complicated formula. A formula is sigma 1 if it is of the form for there is a u such that phi psi, and the psi is already bounded. Similarly, for pi 1, for all u, psi have only bounded quantifier. Sigma 2, there is a u such that for all v, psi will be bounded. Pi 2 similarly. And now you can have so many quantifiers before as you want. Sigma n formulas are formulas of, as you can see. This, Here, a series of n quantifiers started with existential and then changing with universal quantifier, alternative quantifiers, similarly pi of n. And a set of natural numbers is sigma 1. If there is a sigma 1 formula, this one variable that defines this sets in natural numbers. Similarly for pi n, pi 1 set and say sigma 17 set and so on. A set is delta I if it is both sigma I and pi I. Has two definitions, one being sigma I formula, a second being pi 2 formula. And he says that a subset of natural numbers A is recursive if and only if it is delta 1. And it is recursively enumerable if it is sigma 1. And I say that a set A is a set of natural numbers is recursively and reducible to a set, another set of natural numbers. If there is a recursive function such that A is the set of all n, such that phi n is in B. just recognize that some element is in A, you take the baby image by F and look to B. A sigma I complete if it is a sigma I set, and each sigma I set is recursively reducible to the set A. Similarly, of course, for pi I. And now one can prove that for each positive I, there is a sigma I complete set, that's a pi I complete set. And of course, a sigma 1 set is not recursive, similarly for pi I set. And sigma I plus 1 complete set is neither sigma I nor pi I, similarly for pi I plus 1 complete set. On the other hand, each sigma I set is obviously both sigma I plus 1 and pi I plus 1 and so on. And these can relate these notions not only just the set of natural numbers, but by words. We can code words of a finite alphabet by numbers in a usual way. And one remark, if T is a predicate language having at least one as this binary predicate, then the set of all formula probable in this Boolean in just Boolean logic is sigma 1 complete set. Corsair Robinson's axioms, I mentioned that it has. It's better? It's better? Has finitely many axioms, where we can repeat one axiom. Robinson arithmetic has not only the standard model, but also several non-standard models. And we can show that each sigma 1 formula true in N is provable in Q, and hence true in each model of Q. It is sigma 1 completeness. More about Robinson arithmetic. The standard models are just 1, 0, 1, 2, and so on, and the successor of 0. Yeah. Now, this was very quick repetition of things you possibly all know. Now, let us switch to all what I said till now concern classical two-valued logic. Now, let's turn to many-valued logics, in particular to fuzzy logic. If you say fuzzy logic, it can mean, in fact, two things. In wide sense, it is very broadly used by several people that have no relation to logic. It is just any use of the notion of fuzzy sets. I should remind that a fuzzy set is a set such that for each x, we have some degree in which it belongs to the set. It can be 0, it can be 1/2, and so on. Just fuzzy set. And just any use of this notion of fuzzy sets, for example, being fat, more or less, can have degrees. And in this very wide sense, it has been very much used under the name fuzzy logic by non-logicians, but till now it has no relation to logic. You have fuzzy sets, and you make various applications. The question is, my question was, if one can build a bridge between the notion of fuzzy sets to mathematical many-valued logic, and I shall sketch how it is done. What we get is a comparative theory of truth, which can, for example, also be related to logic of vague propositions. doing this mathematical fuzzy logic, we get new insights into on deduction, preservation of truth, and other similar things. And I would like to sketch this notion of mathematical fuzzy logic, and just you will hopefully believe me that is good mathematical and also philosophical logic. Yes. So, fuzzy logic. The author of the name fuzzy set is Lotfi Zadek, 65, and he works published also during the time later, later. Here we have some names that just contributed to the theory of fuzzy sets, and there are very many other names that could be mentioned. Concerning many-valued logic, I think that I'm right that the first person publishing on many-valued logic is Lukashevich, 1920. And the paper Lukashevich-Tarski, 10 years later, they showed completeness of this logic. Hating, Gödel, Moisil, and other names that you see here. Gottwald has a book about many-valued logics. Yes. So what about mathematical fuzzy logic? Pardon? Yeah. I think the first paper about mathematical fuzzy logic was by our Chekhov Pavelka in 1979, and then there are other authors, Takeuchi, Tiani, Gottwald, Höhle, Baas, Mundici, Ivis, Esteva, and Godo. And I have a book, a monograph from 1998 called Meta-Mathematics Fuzzy Logic, and the book has got some very good acceptation, has very many citations, and yes, I shall sketch now the main notions of this, say, mathematical fuzzy logic. So one has some design choices. So the real interval, real unit interval is taken to be the standard set of truth values, comparative notion of truth. The truth can be 1/2, 3/4, and so on. And the logic is truth functional. There are also non-truth functional fuzzy logics, but our logic that I developed is truth functional. Connectives are interpreted via their truth functions. And the truth functions are defined using the notion of a continuous T-norm. Such an operation star on the unit interval is a T-norm. It is commutative, associative, non-decreasing in each argument, and one is its unique element. Yeah. And here you have 3 basic examples: Lukashevich T-norm, Gödel T-norm, a product T-norm. The truth function of implication is defined as a residuum of the corresponding T-norm. You say it is. You see here it is maximum of all z such that x star z is less than or equal to y. It is equal 1 if x is less than or equal to 1 for any T-norm. For x bigger than y, it differs. For example, having x bigger than y, Lukashevich implication from x to y is 1 minus x plus y, Gödel, y, and product just fraction. Negation is defined as x implies 0, minus negation is defined as 1 minus x for Lukashevich, Gödel, and product. The negation of 0 is 1. Excuse me. For Lukashevich, negation is as I shown here. For Lukasiewicz-Gödel, product negation of 0 is 1, and minus x is equals 0 for x bigger something. Forget it. I think there is some mistake on this slide. Now, basic fuzzy propositional logic, BL, has usual language variables, connectives, strong conjunction implication, truth constant 0, and given a continuous T-norm, you can evaluate variables by the truth values. You can compute the value of the formula. A formula is a star tautology, star again being the continuous T-norm, is a formula which has value 1 for each evaluation. And the T tautology, if it is a tautology for any continuous T-norm. Here you have a series of axioms that if you take any of them, you will find them very natural, or are of course also classically probable, but this is not there. This doesn't imply all classical formulas. Deduction rule is modus ponens, and now you have some concrete logics for concrete T-norms. For Lukasiewicz logic, you just add the axiom of double negation, non-phi implies phi. For Gödel logic, you get idempotence of conjunction. For product logic, you have some other axioms which, in fact, express cancellation by non-zero truth value. Scintilla has a simplification. Now, I can show that this basic logic proves exactly all T tautologies, and the strong logics, Lukasiewicz proof exactly all Lukasiewicz tautologies, Gödel. This Gödel tautology is product tautologies. Yeah, and we can here define also some other connectives. Negation is one, phi implies 0. Min conjunction, so or inf conjunction is defined as phi. This conjunction, phi implies psi. This conjunction is not idempotent. And here you can define also supremum by such a formula here. This was standard semantics, just given by T-norm on 0, 1. General semantics is by BL algebras. You can take the continuous T-norms, the corresponding algebras, and generate by this variety. And you can prove completeness of BL with respect to all BL algebras. And similarly for the strong logics, for Lukasiewicz with semi-algebras, and so on. So this was all the propositional logic. For predicate logic, the situation is, as expected, more complicated. So with usual language, predicate variables, connectives, quantifiers, and semantics is given by structures having some domain, interpreting predicates, and say another predicate is interpreted by assigning to each n-tuple of element of some truth value from your chosen set of truth values, and similarly some constants. Truth value is denoted as written here. Now it has usual extension, usual definition of truth value of complex formulas. It is clear what is a value of atomic formula, and for conjunction and implication, you just have the corresponding truth functions of conjunction implication. Well, look at usual universal quantifier. The truth value of for all x phi is infimum of all values of this formula by letting letting the value of x vary over your domain. Similarly, existential quantifier is defined as supremum of truth values of the instances. Axioms of quantifiers look here, also very natural axioms. Look at the third one. For all x, chi implies psi, implies that chi implies for all x psi. Here is assumed that the chi doesn't contain freely the quantified variable. It is not written here, but it should be written here. And you can prove completeness of this predicate logic with respect to so-called safe interpretations over linearly ordered algebras. This very simple notion, I can just wave the notion of success safeness. Now, take a continuous theorem star, the set of standard tautologies of this star is the set of all sentences in the language of predicate basic logic having the truth value 1 for this chain 0, 1 with this continuous t-norm and any structure over this. And general tautologies of star, standard tautologies. And general tautologies is a set of all sentences having truth value 1 for each linearly ordered algebra in the variety generated by the 0, 1 star and each structure over this structure, over this domain of truth values. Generally satisfiable formulas are formulas having truth value 1 for at least one chain linearly ordered algebra and in the variety generated by the continuous t-norm algebra and at least one structure over this algebra. Similarly, standard tautologies of standard satisfiable formulae you have a K which is a, pardon? K is a set of continuous t-norms, and you have just investigate for formulae of evaluation over these algebras given by these stars from K. Similarly, standard positive tautology, standardly positively satisfiable formulae, all standard, because of 0, 1 with some continuous t-norm, maybe several continuous t-norms, but only on 0, 1. General tautologies for each star, the set of general tautologies, which you know what it is, just you can generate a variety by this algebra, by this continuous t-norm structure. It is sigma 1 complete. And also for a class of T-algebras generating the basic algebras, the set of these general tautologies is sigma 1 complete. General satisfiability for each continuous t-norm, the set of all generally satisfiable formulae is pi 1 complete. So general positive tautology similarly, it is sigma 1 complete. Generally positive satisfiability gives you a pi 1 complete set. And now concerning standardness, you see, for Lukashevich logic, Lukashevich t-norm, the set of standard tautologies of predicate logic is pi 2 complete. For Gödel, it is sigma 1 complete. For any star different from Gödel's t-norm, this set is pi to hard, and for all of them except some 6 ones, it is even non-arithmetical, outside the arithmetical hierarchy. Similarly, for standard satisfiability and standard positive satisfiability, and this needs some theory of this continuous t-norm that I shan't explain here. What I offer you is this table, you see, of complexity of standard semantics. So you see we have one tautology is one satisfiable, positive tautology is positively satisfiable. You see that for basic logic, all these classes are non-arithmetical, so complex outside the arithmetical hierarchy. For Lukashevich, it is pi 2 complete, one tautology is pi 1 complete for satisfiable, sigma 1 complete for positive tautologies, sigma 2 complete for positively satisfiable. For Gödel, it is simpler. Sigma 1 complete, pi 1 complete, sigma 1 complete, pi 1 complete. For product, everything is again completely complex, absolutely non-arithmetical sets. And here are some other things that I just delete because I define. You can have t-norms that are composed from various t-norms. Just we shall omit these lines. And I also omit this. Now, one more remarks on mathematical fuzzy logic and natural numbers. We take the Robinson's arithmetic Q. Q minus is a version of this arithmetic where you replace the operations by ternary predicates. A, X, Y, Z for sum and multiplication. And as Schrader showed, this logical Robinson arithmetic is interpreted in his function-free version so that this Q minus over classical logic is essentially undecidable. And we can show it's not just trivial, but it is true that the fuzzy version of FQ minus is a still weaker theory, and also this fuzzy Q minus is essentially undecidable. We have still time. Now we can discuss some various things concerning this fuzzy logic. From classical logic remain Peano arithmetic, a successor, addition, multiplication, zero, equality that can be also replaced by predicate. We have Robinson axiom plus induction scheme. It is written here not an axiom, but as a scheme which is classically equivalent, but for many-valued logic we shall need this scheme, not just the axioms. And if you extend over classical logic, Peano arithmetic by a unary predicate really being true, allowing the formulas containing this truth predicate in the induction scheme, you postulate the dequotation scheme phi, if and only if phi is true for each closed formula, then the resulting theory is contradictory due to the liar paradox, because using some Gödel technique, we can find a formula which in this theory is provable that lambda equivalent is all false in it. Lambda equivalent non-true lambda bar. Therefore, this is Boolean, over Boolean logic inconsistent. If you add these axioms to Peano arithmetic over classical logic, it is inconsistent. Now, what happened? Sorry. What happens in many-valued logic? Can we keep the arithmetical operation is crisp, but allow some fuzzy truth predicate, what can we get? So we have now Peano arithmetic over Lukashevich logic, in which you postulate that arithmetical operations and equality are crisp, can only have value 0 and 1, and axioms of Peano arithmetic. So it is just classical logic inside many-valued logic. Now you add to this, still over Lukashevich logic, add to this classical Peano arithmetic new unary predicate for truth and the dequotation scheme. Phi, if and only phi is true, no, not insisting on crispness of this truth predicate. This can be many-valued. So you have this Robinson arithmetic over Lukashevich with truth predicate. And the Main theorem has one negative part and positive part. So the negative part says that the standard model of arithmetic, the standard model of natural numbers, cannot be explained, cannot be expanded by adding a fuzzy relation, interpreting the truth predicate, such that this will be a model Lukashev Peano axioms plus this truth axiom. Just there is no standard model of full dequotation. But the positive part is number 2. One can show that the theory Peano over Lukashevich with truth predicate is consistent over Lukashevich and hence has a model. Each model of Peano arithmetic over Lukashevich with truth predicate is non-standard. It means its crisp arithmetical part is not isomorphic to standard numbers. It is bigger. It is non-standard model. And now, possibly the last topic. Oh, I shall see. Very true. There is Zadek mentioned such things like very true, quite true, as fuzzy notions. Some lady called Susan Haag protested, saying that fuzzy logic is deviant logic, fuzzy truth values are unjustified, unnecessary. No, this lady should read my book, where she will find that it is, fuzzy logic is a deep, reasonable, many-valued mathematical logic. And as poor logicians, we can ask if these notions like very true have a natural axiomatization over fuzzy logic, and this I shall mention how it is. So you can have very true as a new connective. Very true phi is very true is a connective like negation, for example, just unary connective. And let's first investigate the predicate calculus. We enrich the language by new unary connective of very true, and we extend the basic logic by this connective and 3 axioms. One saying, if phi is very true, then phi. And the second say, if phi implies psi is very true, then if phi is very true, then psi is very true. And 3 says that this junction is very true, then either phi is very true or psi is very true. Deduction rule, as usual, quod modus ponens, and truth confirmation, namely from phi infer very true phi. And this is, the axiom is reasonable. V1 says that very true phi implies phi V2 says that if phi and phi implies psi are very true, then so is psi. Similarly for this junction. Now, it defines what it means that such that a new hedge is star regular. It means if it presents sort of, commutative implication. Very true, x implies y, less than or equal to vx, very true, x implies very true y. It means that the formula VE2 for the previous slide, VE2 you see here, is a tautology, if it is regular. It is true stressing this connective V2. If it is regular, for 1 has value 1 and is subdiagonal. It means very true x and is less than or equal to x. And now the lemma says that this logic in this form is star sound for a hedge if and only if the interpretation of the connective is truth stressing. And a truth stressing hedge is, of course, non-decreasing. Examples. In each theorem of logic, you may define very true phi to be phi and 5. I remember that this connective, a strong conjunction, is not idempotent. So that phi and phi is less than or equal, the value of phi and phi is less than or equal to the value of phi. In product logic, you can have u times u. And there are some other examples that possibly I shouldn't go to too many details. But what I at least say, that if you have a theory over this basic logic with connective very true, we have completeness. The theory over this logic proves phi if and only if for each BLVT chain and each model over this L, for this L, we have that the formula is true in this model. So probability equals truth. I have one more thing. Probably. You see, probability is not and cannot be understood as an assignment of truth values in the sense of fuzzy logic, because you see, still we have some bridges between probability and fuzziness. Namely, temperature is high, is a fuzzy notion. How much high? Similarly, probability is high, over act as a fuzzy modality. So that we may have propositional logic is two kinds of formulas. Non-modal formulas as before, and modal formulae form P phi, where phi is any non-modal formula, and phi, P phi is read, phi is probable. So that phi is probable is a fuzzy notion, more or less probable. Yeah? And this is a reasonable axiom. Probably phi, or non-phi, if and only if non-probably phi. Probably phi implies psi, implies if phi probable, then psi probable. Similarly for this junction. You have classical logic for non-modal formula, formulas, axioms, Lukashevich logic plus these three axioms, phi 1, phi p1, phi p1, phi p2, phi p3 for a modal formula a deduction rule as modus ponens and necessitation from phi infer probably phi. You get a logic complete with respect to the semantics. Now, a telegraphic overview of, say, mathematical fuzzy logic. My conclusion is that fuzzy logic in narrow sense, mathematical fuzzy logic, is a logic with a comparative notion of truth. It is mathematically sufficiently deep, inspiring, and in quite quick development. Papers are appearing in respective logical journals. Monographs exist, mine and also others. The bridge between fuzzy logic in the broad sense and pure symbolic logic is being built, and the results are promising. And if I'm not wrong, it is the end. Thank you.
Thank you so much for the swift and clear overview of fuzzy logic.
There was a lot of technical material that probably I didn't grasp immediately, but I was wondering about the Susan Hack objection. Could you say something more? Because it's, you know, I always saw fuzzy logic used in philosophy, or in artificial intelligence, or in those kind of contexts, and I'm really surprised that she said that it was not interesting. And I mean, I didn't really get what she said, so could you explain?
Is it a known person, this Susan Hack?
I don't know whether she's old, but, sorry?
No, I only ask if it is a famous, known philosopher.
Yeah, I mean, I heard her, I mean, I don't know her work, but I heard her name very often. And
so you see, this is, I know nothing about her except this quotation that I read somewhere, yeah? And I just mention it because it shows how some people can have absolutely false, unjustified relation to fuzzy logic. Yeah.
But what she said.
Aha, you say it is old quotations. I don't know.
Could you put the quote back up, remind us what she said? A book that logic is very old.
Yeah, that was from the mid-70s.
A few years ago now.
But nevertheless, some present criticists of fuzzy logic just quote this quotation of Susan Hack. Yeah, it is not much important, but only for, yes.
Since this is a conference on church thesis, I want to ask about the relation, because the results you say were about complexity in the arithmetical hierarchy were all taken from the classical point of view of this hierarchy. But how, if at all, we can apply the idea of fuzzy logic to the idea of computability? Can we talk about very computable, half computable, or something of this sort, or make some hierarchy there and apply the fuzzy idea to a computative theory? And what will be the form of church thesis in this framework?
So first of all, the only thing I mentioned is very true that I axiomatized, yeah. But in church thesis, you see, I don't know how it relates. But yes, for me, church helped us to recognize the notion of computability, non-computability, and now there's degrees, this non-computability. So that, yeah.
So you think it is crisp notion?
What?
Do you think it is a crisp notion?
Aha, as I have it here, computability is crisp and non-computability is, yeah, it means if a set of natural numbers is sigma 3 complete, it's not computable. The set. You can't decide what belongs there and what is, you have no algorithm that decides for each input if it is in the set or not, yeah. That's all. A classical notion, yeah.
What I ask you, do you think that there is any potential in trying to make a distinction, the recording like in the true, to do the same as computer? Do you think that it makes any sense to link this idea together?
Yes. It's a very nice idea.
Very computable, only not very computable, but computable, something like this.
I promise to think about this, but I can't give no clear answer now. Yeah.
I would like to ask about the part on truth predicates. When you said that there is no standard model for the logic with truth predicate. So I would like to ask, what would happen if you would require not just these basic Tarski equivalences, but the axioms which would govern the inductive definition of the truth predicate? So the cases for propositional connectives, and then for quantifiers, and also what would happen if you would add induction? Would it be still consistent in fuzzy logic or not? Could you get some classical consequences like proofs of consistency of the basic theory and some other stuff? Yes.
I'm afraid I shan't be able to give any concrete answer. I think I did write something about this time ago, but I don't remember what it was. So sorry, I can't answer. Sorry, hello?
Quick question, that it concerns the same topic as before, the truth predicate. Does that result, you went a little too fast, I may have missed it. Does that hold for all of the fuzzy logics that you laid out? The theorem about that if you add the Tarski equivalences, then there's no standard model and there isn't, you know.
You see, I have some result about if you add it to Lukashevich logic.
Okay.
And
yeah.
In general, it will be more investigated in the future.
For the other ones, okay, right.
Again, about the treatment of the truth predicate. It seemed to me that at least one of the axioms indicates some weakness in the truth functional approach to fuzzy logic. Because you have here very true of this disjunction is very true if one of the disjunctions is very true. I think that intuitively there are cases in which we feel much more about give higher credibility to disjunction than any two of the disjunctions. So at least intuitively this axiom doesn't seem intuitive to me. So doesn't you think that it's a kind of weakness of the truth functional approach to fuzzy logic? That it's not really truth functional should be.
You see, I somehow used this very axiom of disjunction just by getting the corresponding result of completeness. You see, if you can delete it, why not? It's a different logic.
Follow from the fact that the truth value of disjunction is always the truth value of one of the disjunctions, because it's the maximum always. So you should have it in this logic and think you have no choice. What I'm saying that the idea that it's truth functional here might be wrong. I think this suggests.
But you see,
you can accept it or not.
In general, the truth value of disjunction is not necessarily maximum, but just supremum, yeah? Because you also have truth algebras of truth values that are not linearly ordered.
Yes, right.
What happens then?
Okay.
Maybe what I have here just applies only to linearly ordered systems of truth degrees, truth values.
I see. Okay.
just a remark in connection with the question on the connection between fuzzy logic and the Church-Turing thesis. The results by Turing and Gödel can be phrased in terms of probability theory. That has been done by Gregory Chaitin. And this might form a connection to fuzzy logic because there's also a connection between fuzzy logic and probability, as you indicated. So there might be a connection in that way.
Very interesting. It should be somehow analyzed. But I wanted to stress that probability is not fuzzy connective because yes, but only I have some relations that I showed here. Yeah.